Hello and welcome. In this video, we're going to be doing the work and energy for the Mechanics Maths A-Level course. I'm going to start by fully explaining to you what you need to know regarding the work energy theorem. It's a nice slow Sunday, so let's do that, and then we're going to solve lots and lots of questions so you guys can have the practice that you need. All right. First, we're going to start by the question that we are going to use for all the past paper questions. Okay, this is an amazing equation. It's called the work energy principle. First of all, you know that work is force times distance. Okay, and you know that there are types of energies. You know that there is a kinetic energy, which is equal to half times the mass times the speed squared. And we know that we have gravitational potential energy, which is mass times g times the height moved by the object. To write down the work energy principle, it goes like this. It's basically work in minus work out of a system equals the change in kinetic energy of the system plus the change in gravitational potential energy of the system. Let's go through each term one by one. This equation is valid for all questions. That's why I like it. Work in is basically any work done by an external force that's giving energy into my system. What do I mean? An example would be a pushing force. 10 newtons. This pushing force is giving energy to my system. If my system is this particle, then 10 newton is going to be a pushing force. So how do I calculate the work in? Let's say it moved 5 meters. So the work in is going to be the force, the external force, which is 10 newtons, that's giving energy into my system, multiply the distance that my system moved. Okay, so this is going to be work in. Okay. However, let me tell you an example. Let's say if we have the ball and it's falling down, you tell me, okay, the weight of the ball, which is, if this is 5 kilograms, then the weight is going to be 5 times g. This weight of the ball is going to act like work in, because it's a force that's causing the ball to move downwards, right? I tell you, good thinking. However, we do not include the weight forces in this work in equation. That's why I told you it's any external force. The word external means that it's not within the part, it's not the weight. Okay, why? Because in this equation the weight factor is accounted for here in the JPE. Okay, so again, work in is any external force, not weight, that is giving energy to my system. Work out is very similar. However, it's any external force that is taking energy away from my system. Okay, so if the particle is moving on a road and it has like 10 newtons of friction and it moved to the right 5 meters, then the work out is going to be 10 times 5. So it's any external force that's taking energy out of my system. Changing kinetic energy is basically half mass times V final squared minus half mass times V initial squared, or we can rewrite it as half mass times V final squared minus V initial squared, plus change in gravitational potential energy is mass times g times change in height. Okay, if the particle started here and its final height is above where it started, then this delta H is going to be positive. And if it started here and its final height is below where it started, then it's going to be negative. And that's basically all you need to solve 90% of the work energy related question. Now, let's jump straight into the questions. Let's do the first question. But before that, I want to come and bring to your attention that I've done a full mechanics course. Let me show you. If you read the title of this course, it says Mechanics Mastery Alternative to Tuition or Alternative to School. This course is intended to eliminate the need of tuition, expensive tuition, eliminate the need of school. So if you literally go through this course, okay, go through everything, this course has explaining on every single mechanics topic. This goes for both Edexcel and Cambridge, and it has solving. On each chapter there is solving, and you will notice that the solving videos are usually longer because I want to focus on solving as many questions as I want, because this is what actually makes a difference. As you can see, everything is explained and solved, and then at the end I have full past papers solving, just me going through past papers and solving them, recent ones, and I'm going to have a summaries and keywords section with some resources for you guys in order to download. This is the summaries. Okay, it basically summarizes every single assumption and what it means, and it's me explaining literally everything on the same whiteboard that I'm doing these. However, this is a comprehensive course. It's 16 hours total. It's amazing. Please, I'll leave a link to it on the description. Feel free to go check it out, and I'm going to leave a discount code to people who email me. So email me, I'm gonna send you a discount code if there are discount codes still available. Now, let's attempt this question. This question says a particle P of mass 0.4 kilograms is projected vertically upwards from a horizontal ground with a speed of 10. Find the greatest height above the ground reached by P. So in this question, the particle is projected vertically upwards from a horizontal ground. This is the horizontal ground. And the particle is projected vertically upwards, giving a speed of 10 meters per second. The greatest height. So this object started with some kinetic energy because it's moving. And as it goes up, this kinetic energy is going to change into gravitational potential energy. When all the kinetic energy changes to gravitational potential energy, the object is going to reach its maximum height, and then it's going to start going back down again. Okay, so basically half kinetic energy is going to equal mgh. Okay, I can cancel the m. I'm gonna have half times 10 squared equals g, which is for Cambridge, g is 10, and h is the thing that I want, so 10 can cancel with 110, so half times 10 equals height, so height equals 5 meters, and this is the answer. Now, part P says, when P reaches the ground again, it bounces vertically upwards. So it's going to fall down, bounces vertically upwards. At the first instant that it hits the ground, P loses 7.2 joules of energy. So what happened here is that P was moving down, and then when it hit this ground, it's going to bounce, and this impact is going to cause it to lose some energy. So how much energy did we lose? We lost 7.2 joules. So let me ask you, if it went up and then it went back again, that means that all the mgh, or gravitational potential energy, changed back again into half mv squared. So it's the same thing, and h is 5. You're going to find v is the same as the original v, 100%. And if you want to make sure, you can do that. So m and m will cancel. You'll have 10 times 5 equals half times v squared. So this is 50. 50 equals half v squared. So 100 equals v squared, so v equals 10. Yeah, so now it has a speed of 10 as it falls down. Okay, so its kinetic energy at this position, when it's down at this position over here, is half times mass, which is 0.4, half m, times the speed squared, right? This is the kinetic energy. After the impact, it lost 7.2 joules. So this kinetic energy after the impact is going to lose 7.2 joules. And if we put that on the calculator, it's going to give us half times 0.4 times 10 squared minus 7.2 is going to give us 12.8 joules, and this is the remaining energy after the bounce, because just before it bounces it was moving with this energy, and after it bounces it lost this, so basically we remained with this energy. So now we are at this point where the object already bounced, it lost 7.5 and is going up again, and now it has 12.8 joules of energy, right? So if we want, question wants the time between the first and second instance at which P hits the ground. So it wants the time from the first bounce, so literally this position over here is going to go back up again. However, it's not going to go to 5 meters because it lost some energy, right? It's going to go back up and then back down again. And the question wants the time as it goes up and down. So how we need to do that? First, we need to calculate the speed that's going up here after the initial bounce. And let me ask you, do you think the speed is going to equal 10 or is it going to be lower? If you said lower, yes, you are correct, because the kinetic energy now is just 12.8, okay? And that's going to equal half times 0.4 times the new velocity squared. If we solve for v squared times 2, so 12.8 times 2 over 0.4, I'm multiplying this 2, dividing by 0.4, and then square rooting to get v square root of 12.8 times 2 over 0.4. That's going to give me a velocity of 8 meter per second. So this is now the velocity, right? To find the time, now this is a kinematics equation, okay? And by the way, I've done a full revision on kinematics as well. I'm going to leave the link to it on the top right hand corner. Go check it out. So in order to solve this using kinematics, I like to always list down what do I have. So the initial velocity is going to be the velocity as it goes up, which we calculated as 8 meter per second, okay? The acceleration is going to be, if I'm taking the direction of upwards as positive, then acceleration is acting down, so it's going to be negative 10 meter per second squared. And the displacement, I'm trying to find the time it goes up and then back again. So I want to find when it reached here again. So the displacement is basically 0 because it started at the same position. And again, I explained this thoroughly in the kinematics revision video. And what do I want? I want the time that all of this happens. So initial velocity, acceleration, displacement, and time. The only letter I didn't mention is the final velocity. So I'm going to use the kinematics equations, the Saviot equation, the constant acceleration equations for the one without final velocity. So it goes like this. S equals ut plus half at squared. So S is 0. U is 8 times t plus half times acceleration, which is negative 10 times t squared. Half times 10 is negative 5, so I'm going to have 0 equals 8t minus 5t squared. What I can do here is I can take a t out. I'm going to have 8 minus 5t equals 0. So that gives me two answers, t equals 0, which is expected because at the beginning it also was at this displacement, which is 0 displacement. And the second answer is when 8 minus 5t equals 0. So moving, let's erase a little bit. Moving and solving this, I'm gonna have 5t equals 8. So t equals 8 over 5, or basically 1.6 seconds. This is the time it will take to do all of this maneuver. Yeah, good. Now, let's move to the next question. It tells you a particle of mass 1.6 kilograms is dropped from a height of 9 meters above horizontal ground. The speed of the particle at the instant before hitting the ground is 12. Find the work done against a resistance. Let me ask you, work done against a resistance, is it work in or work out? We write our work energy principles, work in minus work out equals change in kinetic energy plus change in gravitational potential energy. Work done against a resistance is work out. This is what I'm trying to find. Okay, work in. Do I have any external force that's giving energy into my system? Do I have any force that's pushing it? Tension that's pulling it down, or some sort of force? No, I don't have a force, and work is force times distance. So if force is 0, work in is also 0. Minus work out, this is what I'm trying to do, equals the change in kinetic energy. So it's going to be half times mass times velocity final squared, which is 12, minus velocity initial squared. It's dropped, so it means it started from rest, so initial velocity was 0, plus change in gravitational potential energy, which is mass times g times height. However, height here is 9 meter. The object started here, it ended up below its starting position by 9, so delta H is negative 9, and from here we can solve for work out. Okay, if we do all of this on the calculator, half times 1.6 plus 1.6 times 10 times -9, that's gonna give me -28.8. So cancelling these two, work out is going to equal -28.8 joules. This is going to be my answer, and this is how to apply the work energy principle. This is our first time applying it. Okay, this was an easy 3-marker. Let's take it up a notch and try to solve harder questions. Now, this question says a cyclist is riding a bicycle along a straight horizontal road AB of length 50. The cyclist starts from rest at A and reaches a speed of 6 at B. The cyclist produces a constant driving force. Let me ask you, this driving force, it's an external force that gives energy into my system. So it's going to cause work into my system, okay? So the constant driving force is 100 newtons. There is a resistance force as well. So that tells me that I will also have a work out. And the work done against this resistance force, so the work out due to this resistive force is 3560. Find the total mass. So let's write our work energy principle equation. Change in kinetic energy plus change in gravitational potential energy. Okay, work in is going to be the driving force, which is 100, multiply the distance it moved. What did it move from A to B? 50. 100 times 50. Minus work out, it already gave us the work out. If it gave us the force, the resistive force, we need to multiply that resistive force by the distance. However, since it gave us the work done, work out straight away, we just plug it in. 3560. That's going to equal half times mass, which is the thing that I want to get, times velocity final squared, which is 6 squared, minus it started from rest, so velocity initial is 0 squared, plus did it go up, down, it just moved on a horizontal road, so it started here and then it ended up here, so there is no movement up or down, there is no delta H, so GPE is mg times 0 or just plus 0. So from here that's 500, let's do 500 minus 3560, so that's going to give us negative 3060 equals 6 squared is 36 times half is 18, so that's going to be 100 times 50 is 5k, it's 5,000. So 100 times 50 minus 3560, that is 1,440 equals 18m. So dividing both sides by 18, 1440 divided 18 is basically 80, and never forget the units, so it's 80 kilograms. Okay, now we're going good. Let's do the next question. Okay, this question is interesting. It tells me the diagram shows a vertical cross section of a surface. A, B, and C are 3 points on the cross section. The level of B is h meter above the level of A. The level of C is 0.5 meters below the level of A. A particle of mass 0.2 kilograms projected up the slope, so it started from here, and it's moving with a speed 5 meters per second. The particle remains in contact with the surface as it travels from A to C, so it doesn't shoot up over here. No, it goes like this, and then it's basically attached to the surface. Okay, given that the particle reaches B with a speed of 3 meters per second and there is no resistance force, so that tells me that there is no work out. Find H. So let's write it again. Work in minus work out equals change in KE plus change in GPE. So let's see. Is there any external force that's giving energy into A? Is there any pulling, any tension, any pushing? No. So the work in is 0. Minus, is there any work out? Is there any force that's taking energy away from the system? Is there any friction? It says no resistance forces, so work out is also 0. That's going to equal half times the mass, which is 0.2, times the velocity final squared, which is the velocity at B, so 3 squared, minus the velocity at A, which was 5 squared. So the velocity final minus the velocity initial plus change in gravitational potential energy. So it's going to be mass times g times the change is going to be the height. This height is above, so it's going to be positive h. From here, what we can do is we can multiply this out. So half times 0.2 times 3 squared minus 5 squared is going to equal, so 0 equals negative 1.6 plus 0.2 gh. Moving this to the other side, 1.6 equals 0.2 gh. So h is basically equal 1.6 over 0.2 times g. So 1.6 over 0.2 times 10, that is going to give me 0.8 meters, and this is the final answer for h. Okay? Let's do part B for this question. It says that it's given instead that there is a resistance force and that the particle does 3.1 of work against that resistive force. This 3.1 joules, is it work in or work out? You said work out, you're absolutely correct. And the question asks you the resistance as it travels from A to C. So A is our initial point, C is our final point. So let's again write the work energy equation. It's already written over here. So let's figure out what is work in. Do I have any work in? Still no force that is giving energy into my system. Do I have a work out? Yes, it's minus 3.1 joule. It was given in the equation. That is going to equal the change in kinetic energy. So it's half times mass times v final squared, which is the thing that I want. I want the speed of the particle when it reaches C. I don't know it. The v final is the v at C, minus the v initial, which is at A, which is 5, minus 5 squared, plus change in gravitational potential energy. So it's 0.2 times g times h. What is h? What is the difference in height between A and C? You don't regard anything else that happened. You just see the first initial point and the second initial point of your, the initial point and the final point of your system, and that's it. So the difference in height is 0.5 meters from A to C. It's below from where I started, so it's going to be negative 0.5. So negative 3.1 is going to equal half times 0.1, 0.2 is basically 0.1. Applying it inside, that's 0.1 v squared minus 5 squared times 0.1 is 2.5 plus 0.2 times 10 times negative 0.5 is basically negative 1. So negative 2.5 minus 1, that is negative 3.5. Moving this to the other side becomes minus 3.1 plus 3.5 equals 0.1 v squared. Dividing both sides by 0.1, this cancels, and square rooting in order to get v. So v is basically this value. So square root of negative 3.1 plus 3.5 over 0.1. That's going to give me a velocity value of 2 meters per second, or 2 ms power negative 1. This is how to apply the work energy principle in any single situation. Now, let's move on to the next question. Yeah, this question over here. Okay, this question is a little bit tough, so let's see how we can approach it together. It says that we have two particles now, P and Q, of masses 0.5 kilograms and m kilogram respectively, and are attached to the ends of a light inextensible string. Light tells me that the tensions on both sides of the string are equal. The tension throughout the whole string is the same. Inextensible tells me that the acceleration on both particles are going to be the same, as well as the velocity at a specific time is going to be the same. And it tells me that if P moved 1 meter down, then Q must have moved 1 meter up. The displacements are also the same for the particles. Okay? These are all written in and compiled for you in the course I spoke about in the beginning. The string passes over a fixed smooth pulley. There is no friction in the pulley, which is attached to the top of two inclined planes. Particles are initially at rest with P on a smooth plane. This plane has no friction and inclined 30 degrees to the horizontal. P on a plane inclined 45 degrees to the horizontal. The string is taut and the particles can move on lines of greatest slope of the two planes. A force of magnitude 0.8 newtons is applied to P, acting down the plane, causing P to move down the plane. It is given that M equals 0.3 and the plane on which Q rests is also smooth. Find the tension in the string. So this is a little bit of a dynamics question. So let's solve it. Let's start by always drawing a free body diagram for both particles. So I'm gonna always start with the weight. So this is 0.5 G. I'm going to have a reaction force, let's call it RP. I'm going to have a tension force in this direction for P. Do I have any friction? No. So let me go on and resolve this 0.5 G. I'm just gonna have two components that are going to be in the axes I'm looking for. My axis basically is going to be, this is going to be the x-axis and this is going to be the y-axis. You always choose these. The x-axis is the parallel to the slope direction and the y-axis is the perpendicular to the slope direction. It's no longer horizontal and vertical. No, this is your new x and y axis, and I've gone through this thoroughly in the course as well. So we need all the forces to be aligned with those two axes. So the only force that's not aligned is basically this weight force. So let's draw two components of the weight. One is going to be like this, one is going to be like that. This angle right here is going to be 30 degrees, okay? Because this is 90, this triangle, this is 90, this is 30, then this is 60 degrees. If this is 60 degrees and this is 90, then this must be 30. Okay? So we start from 0.5, we're getting the component closing on our angle, so it's going to become 0.5 G cosine 30. And then if we're moving away from the 30 degree angle, it's going to be 0.5 G sine 30. Okay, so when you're moving towards your angle, it's cosine. When you're moving away from your angle, it is sine. Let's draw the free body diagram now for Q. So Q is going to have weight down, which is mg. M is 0.3, so 0.3 G. It's going to have a tension upwards. It's going to have a reaction force. Let's call it RP. And also we need to resolve the weight components. This is going to be 45, so this is going to be 0.3 G cosine 45 because I'm closing on this angle. And this, since I'm moving away from this angle, is going to be 0.3 G sine 45. Now, P moves down the plane, so the acceleration here is like this. The acceleration there is going to be of the same value and it's going to be upwards. Now, to find the tension, let us get two equations. Let's resolve particle P first, okay? Taking always the direction. Let's say we're going to apply Newton's second law. So sigma f of x, we're taking this x direction first, equals mass times acceleration, taking down the plane as positive. Why down the plane as positive? Because we always copy the acceleration direction. If the acceleration is downwards, then downwards is the positive direction that we should choose. So sigma f of x means the addition of all the forces on the x-axis. Down forces are going to be positive and up forces are going to be negative. So here it's clear that the 0.5 G sine 30 minus the 0.8 Newton, because they're both downwards, plus the 0.8 Newton because they're both downwards, minus the tension force is going to equal the mass, which is 0.5 times the acceleration. That is our first equation. Resolving particle Q, sigma f of the x direction for particle Q equals ma. Now taking up the slope for Q as positive because the acceleration here is upwards. So what we're going to do is we're going to say that tension minus 0.3 G sine 45 is going to equal the mass, which is 0.3 times acceleration. So now we have two equations that we can solve for the tension and accelerations if we wanted to. Okay, so how will I do that? Let me first rewrite this equation. Let me rewrite it here, but I'm gonna write the negative tension first, and then add 0.5 g sine 30 plus 0.8. So 0.5 times 10 is 5. 5 times sine 30, that's 5 times half, so it's 2.5. 2.5 plus 0.8, that is basically 3.3. So negative tension plus 3.3 is going to equal 0.5a. And I'm going to add these two equations together. By adding them, I'm going to cancel tension. I'm going to have negative 0.3 times 10 sine 45 plus 3.3. I'm going to add this term and this term together. That's going to give me 1.1787, and that's going to equal 0.3 plus 0.5 is 0.8a. Dividing both sides by 0.8, that's going to give me an acceleration value of 1.47 meter per second squared. I'm going to use the acceleration value to get the tension. Feel free to solve it however you want. I just find this easier to cancel the tensions because they're already different signs. So what I'm going to do, I'm going to put this acceleration value in this equation over here. So t minus 0.3 g sine 45 equals 0.3 times acceleration, which is 1.47. So tension is going to equal, basically, I'm going to move this to the other side, 0.3 g sine 45 plus 0.3 times 1.47. Plugging that in the calculator. It's going to give me a tension value of 2.56 newtons, and this is the right answer, and this is how to get your 5 marks. This question comes a lot in exams, maybe twice in the same exam as well. So what we are going to do is we're going to continue for part B. Let's see how we can solve part B. Part B says it's given that instead the plane on which Q rests is now rough, okay? And that after each particle has moved a distance of 1 meter, their speed is this, the work done against friction in this part of the motion is that. Use an energy method to find the value of M. So now things have changed. Let's redraw the whole thing. We had this, we had the pulley, we had another slope. Okay. This was 30 degrees. This is particle P. This is particle Q. They're all connected with a tension or a string. Okay. This is 45 degrees. And now this plane is rough. So there is going to be some friction force over here. Question asks us to use an energy method. So we're going to use the work energy principle. However, let's resolve this in order to see the forces acting. Again, P is going to be very similar. Going to be the weight, which was the weight of P was 0.5 G. There is going to be the tension. There is going to be the reaction force P, and P doesn't have any friction, so that's all we're going to have. No, we still have the 0.8 Newton force that's acting over here. So this is 0.8 Newton. Now let's resolve. The weight is going to have 0.5 G cosine 30 and similarly 0.5 G sine 30. Okay? For Q, things will change a little bit. We're going to have the mass down. Now I don't know what is the mass. I'm going to have the tension force up. I'm going to have reaction for Q. And I'm going to have some friction force. Now I can resolve this as mg. This is 45. So mg cosine 45 and mg sine 45. Okay, now The work energy principle goes like this: work in minus work out equals delta KE plus delta GPE, right? How to approach this? There are two ways. There is an easy way and a more complicated way. The complicated way is basically applying this work energy principle equation on each particle alone. So this is particle P, this is particle Q. If we're going to apply it on particle P moves down the slope, right? So we're going to say work in is going to be any external force that's causing the particle to move. So the only external force that's not weight is 0.8 newtons, and this is, we have tension, but tension here is going to be resistive because the particle is trying to accelerate downwards. Tension is acting as a resistive force, so it's actually going to be included in work out. So for P, it's going to be 0.8, and the question tells me it moved 1 meter minus work out, which is tension, times 1 meter, and it's going to equal change in KE plus change in GPE. And then you will get another equation for Q, which is going to be work in. What is the external force on Q? It's tension. This is causing now work in. However, sir, it was causing work out on P. Yes, because it's opposing its motion. Q is moving up and tension is up. So tension is going to be work in. So work in times distance, which is 1 minus the work out. And it gave you in the equation that the work done against friction is 0.5. Q only has a friction, so that's why this is 0.5 equals blah, blah, blah. This is the hard way because we're going to have two equations that we need to solve. Let me show you another way that basically says instead of taking each particle alone as an individual system and getting equation for both systems, we're going to take both particle as one system. Both of the particles in one system. What's the advantage of this? The advantage of this is that whenever you take the whole system or both particles as one system, you don't need to include the tension effect. You don't need to include the tension in work in or work out because tensions are going to cancel. Because if you remember, tension here was a work out and tension here was a work in. So we had a minus T times 1 in P, and for Q we had a T times 1. So they will eventually cancel. So taking the whole system skips this part and just tells you that I won't include the tension effect. So let's rewrite the equation for both, okay, not including the tension effect. So work in, what is any force that's causing work into the system? That is external, meaning it's not weight and it's not tension at the same time because as the whole system, we took the whole system, so tension effect is cancelled. It's only the 0.8 Newton. So work in is going to be 0.8 multiply the distance, which is 1, minus what is work out of the system, that is external, not weight related and not tension. The only work out is the work done against friction, which is 0.5, right? That is going to equal the change in kinetic energy for both particles. So the change in kinetic energy for P is going to be half times the mass of P times the velocity of P squared. So it tells me the final velocity was 0.6 minus initially they started from rest. They started from rest, not this rest. Okay, but they started from rest. It's given instead of the plane on Q, yeah, because instead, and it tells you according to this part that they were not moving initially, so it started from rest, so minus 0 squared. This is the kinetic energy for P. We have to add the kinetic energy change for Q as well. Don't forget that because we're taking both particles. So half times mass of Q, which is m. Velocity final for Q is going to be the same because it's an inextensible string. So 0.6 squared minus 0 squared, which is basically just 0.6. Plus change in gravitational potential energy. This is a little bit tricky. So let's take P first. P was here and it moved down 1 meter. This is 30 degrees, right? So if we do a triangle, this is 1 meter and this is 30 degrees. P was here and it started as here. So the difference in height is going to be this height over here. So using trigonometry, sine 30 is going to equal opposite, which is height, over hypotenuse, which is 1. So the height is going to be this magnitude of the height is just basically sine 30. So height equals sine 30. So for JPE for P is going to be the mass of P times G times the height. However, it started from here and it ended up below its initial starting point, so it's going to be negative sine 30. Plus GPE for Q. Okay, let's do the same for Q. Q moved 1 meter up, it was here and then started as here. This is 45 degrees. We need this vertical height over here. So again, sine 45 is going to equal opposite over hypotenuse, which is 1, so katoa. So height is sine 45 and it's going to be positive in this case because it moved up relative to its starting point. So it's going to be mass times G times positive sine 45, and from here we have the equation that we need in order to solve. So 0.8 times 1 minus 0.5 is basically 0.3 equals half times 0.5 times 0.6 squared minus 0 squared is equal 0.09 plus half times m times 0.6 squared is basically 0.18 m plus this term is going to be 0.5 times 10 times negative sine 30. That is going to be negative 2.5. And this term over here is going to be basically sine 45 times 10 times m. So it's going to be basically just 5 root 2 times m. Now moving this to this side, and moving this to this side is going to be 0.3 minus 0.09 plus 2.5 is going to equal 0.8m plus 5 root 2m, 0.18. That is going to equal around 7.251 m. Adding all of this and dividing by 7.251 both sides, m is going to equal m is basically, yes, 0.374 kilograms, and this is how to use the energy method to solve. All right, let's continue solve the next question, which is the hardest of all of them. So let's erase this a little bit and start reading the question. So this question says we have two particles A and B of masses 4 and 3 kilograms attached to the ends of a light inextensible string. Again, light means tensions on both sides are the same. Inextensible means accelerations, velocity, and displacements on both sides are the same. Pass over a smooth pulley. The pulley is fixed at the top of the plane, which is inclined at 30 degrees. A hangs freely below the pulley and B is on an inclined plane. String is taut, and the section of the string between B and the pulley is parallel to the line of greatest slope. Given that the plane is rough and that the particles are in limiting equilibrium, we'll speak about limiting equilibrium. Find the coefficient of friction between B and the plane. Again, let's start by drawing the free body diagram. Weight for G, I'm gonna have tension upwards, and over here this is heavier than this, and it's even not on an incline, so definitely it will accelerate downwards, and this is gonna accelerate upwards with the same acceleration. For B, I'm gonna have weight 3g, I'm gonna have a reaction force, let's call it R, and I'm gonna have a tension force. And since this is a rough plane, I'm going to have a friction force as well. So this friction force is going to have a special equation. Friction is going to equal mu times this reaction force. Mu is the coefficient of friction. R is basically this normal reaction force. Why is friction mu R? Because the object is in limiting equilibrium, means it is in equilibrium, however it's about to move, so friction is maximum friction, and maximum friction has a specific equation which is mu R. Let's use this to find the coefficients. Now, these accelerations are actually zero. We don't have any accelerations. They're about to accelerate in this position because we're still in equilibrium, right? So equilibrium means that the forces are balanced. So if I'm resolving for A, let's say for A, I'm going to use the normal X and Y plane because A is not on any incline. Sigma F of Y is going to equal mass times acceleration is going to equal 0 because acceleration is 0. We're in equilibrium. So that means that the forces are balanced. So upwards forces, there is no net force. Upward forces equal downward forces. So tension equals 4G. Now doing the same for B, resolving B, saying that sigma Fy, Y is basically this direction and X is up the slope direction, up and down the slope. Now I have 0 acceleration as well, so it's also equal to 0, so the forces are balanced as well. So over here, I forgot to resolve the weight. The weight is going to have a component 3g cosine 30 and 3g sine 30. Yeah. So sigma Fy in this direction are balanced, so R is equal 3g cosine 30. Now let's resolve in the x direction. So we're resolving particle B. Sigma f of x equal also 0 because the particle is not accelerating even in the x direction. So the forces up is going to equal the forces down. So tension is going to equal the forces down, which is mu times r. What is r? Previously it's 3g cosine 30. Okay. And another force that is down is 3g sine 30. Right? So from here, I know that tension is basically 4g. Tension is 4g. So from here, I can basically, let me cancel a g from each term. And I can say that 4 equals 3 cosine 30 plus 3 times sine 30 is basically 3 divided 2, which is 1.5. 4 minus 1.5 equals 3. This is times mu. Forgot this mu. Times mu. 3 cosine 30 times mu. So if I want mu, I'm going to divide both sides by 3 cosine 30. 3 cosine 30. So mu is going to equal 4 minus 1.5 over 3 cosine 30. That is going to give me an answer of 0.962. This is the coefficient of friction. The coefficient of friction does not have any units. Now, for probably the hardest question for today, it says that it's given instead that the plane is smooth, so there is no friction at B, and the particles are released from rest. So they are released, that means that they will accelerate now. When the difference in the vertical heights of the particles is 1 meter, so initially the difference of the two particles is 1 meter vertically, okay? The question says, use an energy method to find the speed of the particles at the instant when the particles are at the same horizontal level. This is interesting. Let's think about same horizontal level for a bit. Okay, let's zoom in and have a nice discussion about it. Let's say this is where both particles are going to be the same level. A moved a little bit down, B moved a little bit up, and they are basically both at the same horizontal level. This is at the same horizontal level as this. Let's think about what is going to happen. Okay, let's say that the upward distance that B moved, so this distance from here to here, let's call it x. We don't know where is it. Let's just call it x. This whole thing is 1 meter. This part is x, so this part must be 1 meter minus x. So the height that A moved down must be 1 minus x, right? This is the this is what we will work with from now. Okay, so this is what we are trying to find. We are trying to find when they're both at this level. Okay? So let's use so there's going to be 3G, it's going to have a tension, and basically that's it. We have a reaction force, and 3G sine 30 3g cosine 30. This is basically 4g, and this is tension, right? Let's use the energy method. So we're going to use the work in minus work out equals change in KE plus change in GPE. Again, we're going to take the whole system. What's the advantage of taking the whole system? If you remember, we're going to not include the tension, the work done by the tensions, okay? So the work in now, is there any external, and the word external means not weight, any external force that's giving energy into the system that is not weight nor tension? No. So my work in is 0. Is there any work out? Is there any external force that's not weight and not tension, because we excluded tension, that's causing resistance to my system? No. If I'm taking, let's say for example, if I'm not taking the whole system, if I'm not doing this trick and I'm taking A alone, there will be some work out caused by this tension, right? So I'm going to have a tension times the distance that A moved, which is 1 minus x. It's going to make my equation a lot more complicated, right? Same thing for B here. B is going to have a work in, right? Because this tension is going to act as a force that's giving energy to the system, right? So when we're taking the whole system, this is the beauty of it. It's just way easier. So 0 minus 0 equal the change in kinetic energy for both particles. For A is going to be half times the mass of A, which is 4, times the V final of A, which is the speed we're trying to find. Let's call it V, minus the V initial, which is 0. So minus 0 is basically nothing, okay? Plus the change in kinetic energy for B, which is going to be half times the mass times the same final velocity minus initial, which is 0. So I'm just not going to bother to write minus 0 squared. You already know. Okay, plus change in gravitational potential energy of A is going to be the mass of A times G times the height that A moved. A, we said it's going to move 1 minus x, right? And it's going to end up at the place below its starting point, so it has to be minus 1 minus x. This is the change in height for A, right? For B, the change in height is going to be plus mass times G times, what is the change in height for B? It's basically x, right? Now, something that is very interesting that's going to happen here is that it told you that that basically we know, because it's an inextensible string, the distance that A will move down is the same distance that B will move up, because it's an inextensible string. So for B, B is basically moving upwards, and we know that this distance that is going to move up, which is this distance we're interested in, right? It's going to move this distance up. So this distance is basically x, so this is x, and this is 30 degrees. This distance, let's call it d, okay, this distance must be equal to the distance that A moves down, because it's an inextensible string. If A moved down by 1 meter, B will move up by 1 meter. Okay, if A moved down by 1 minus x meter, B will move up by 1 minus x meter. So this D must be 1 minus x as well, right? So from here, what I can do is I can do some trigonometry. I can say sine 30 is going to equal opposite, which is x, over hypotenuse, which is 1 minus x. Sine 30 is 0.5, and I'm going to multiply 1 minus x to that. So 0.5 times 1 minus x equals x. Multiplying this inside, 0.5 minus 0.5, x equals x. Moving it to the other side, 0.5 equals 1 plus 0.5, which is 1.5x. Dividing both sides by 1.5, x is going to equal basically 1 over 3 meters. So this is the distance x. This is the distance x, and from here I can say replace x equals 1 over 3. So any x that I'm going to have here, I'm going to replace with 1 over 3. So this becomes 1 over 3, and this also becomes 1 over 3, right? Now I can solve for v. So left side is going to be 0. Half times 4 times v squared is 2v squared. Half times 3 times v squared is plus 1.5 v squared, plus 4 times 10 times negative, and then open bracket, 1 minus 1 over 3 is going to be minus 80 over 3. And this is going to be basically 3 and 3 will cancel. This is going to be 10, right? So minus 80 over 3 plus 10 is equal to minus 50 over 3. So we can just write minus 50 over 3 here. We move this to the other side. So 50 over 3 is going to equal 2 plus 1.5, which is 3.5 v squared. So v is going to equal basically 50 over 3, divide 3.5 and all square rooted. We put that in the square root, is going to give us a v value of 2.18 meters per second. This question is super interesting, and I'd hope that you take a time to try and go through it on yourself once again. Please guys, note that I'm going to do lots of videos like these. Stay tuned, check out my course, and I have my WhatsApp, also an email in the description. If you need anything, you can let me know. Thank you so much for watching. I hope this was helpful. Check the other videos, subscribe and like, it helps a lot. Have a good day and thanks for watching.